All right, so we're going to talk about three things today. So we have three topics. One, the chi-square goodness of fit test. Two, the chi-square independence test. And three, analysis of variance ANOVA. Okay, so those are the three topics that are on the table. So what we're going to do is I'm going to briefly outline what each of these is used for, and then we're going to look at an example of each one in Rcmdr, because my guess is we'll probably only have time to get through one example of each. So depending on where you are in lecture, you may have heard of one of these things, all of these things, a combination of these things, none of these things. You know, it's not exactly a perfect streamline in all cases, but I know if you're in my lectures in the morning today anyways, you would have seen the first two, and then the ANOVA is coming later in the week. And then if you're in my lectures in the afternoon, you probably haven't seen any of these yet. So I'm going to try and outline them briefly so that you have an idea of what the goal is. And then we will use the illustrations in Rcmdr to work through each of them. Okay, so some similarities. All three are hypothesis tests. Okay. But the differences are that they all test different things. Okay, so with the chi-square goodness of fit test, we basically have the following. So on step one, we have H0, the data follow some pre-established pattern versus HA, the data do not follow this pattern. Okay, on step two, we have state alpha. On step three, we have compute test statistic. Okay, so here the test statistic is x squared is equal to the sum of observed minus expected squared over expected. So, and then just to be clear, this sum is across the whole thing. Okay, so we have to learn how to compute these observed and these expected counts. All right, so O are observed counts, and expected are expected counts. And these are given by E is equal to little n times P, where little n is the sample size and P is the probability associated with each of the different outcomes in this pattern that we are looking at. And I'll show examples of this in the illustrations in Rcmdr. And then on step four, we have critical value or p-value. And this is on degrees of freedom is equal to C minus 1, where C is number of categories. And then on step 5, we have decision. And then on step 6, we have conclusion. Okay, so the test runs just like any other hypothesis test that we have seen in the course. The big difference here is that these particular tests, so these chi-square tests, they are very much unique to the question that they are asking. So we're only going to use a goodness of fit test when we have one variable that is of interest to us, and we want to determine if that variable is giving us evidence that some pre-established pattern regarding a particular distribution is actually being followed. So this is sort of the same thing as what you could think of as a one variable chi-square test. And again, I'm going to show you illustrations of this in a little bit to try and help you associate this test with a particular set of data. And you will see these same illustrations in the lectures as well. So this test is very much for one particular type of problem. The next chi-square test is very much for a completely separate type of problem. Okay, so in the second case, where we have the chi-square goodness of fit test, we have here on step 1, H0, 2 variables are independent versus HA, 2 variables are not independent. Okay. So the first test, which was the goodness of fit test, that is utilized when we want to establish if one variable follows a pre-established pattern. So it's a one variable goodness of fit, or one variable chi-square test. The second chi-square test, which is not the goodness of fit test, but the independence test, okay. The chi-square independence test is used when we want to determine if two variables are independent of one another. Okay, so this would be the two variable chi-square test. So on this test, on step 2 and step 3, we have the exact same thing that we had above. Actually, all of this is the same except for the degree of freedom count and the expected value count. Okay, so on step 2, we have state alpha. On step 3, we have the computation of the test statistic. Okay. Now, the expected values here are equal to, in the goodness of fit test only, the expected values are equal to what's little r minus 1 times little, or sorry, losing my mind, is equal to capital R times capital C over little n, where capital R is row total and capital C is column total, okay? Now, as I said, once we get into the illustrations using Rcmdr, I will show you exactly what I mean by row total and column total. But the thing to keep in mind here, and this will become clear through illustration if you haven't seen an example of this already, is that the chi-square independence test is almost exclusively used on contingency tables. So when I'm talking about a row total and a column total, I'm talking about the row totals for a contingency table and the column totals for a contingency table. So those two outcomes from that table. And then the degrees of freedom for this test is the number of rows minus 1 multiplied by the number of columns minus 1. Okay, so just the count of rows minus 1 times the count of columns minus 1. All right, so for both of these tests, we have effectively the same outline. We have the same set of assumptions that are also attached to the test, and I'll I'll work through those assumptions via the illustrations, but I just wanted to give you an idea of how the test proceeds in the chi-square case and sort of what you can expect in terms of differences between them. So again, they are both using the same distribution, which is a chi-square distribution. I'll talk a little bit about this once we get into the Rcmdr stuff. And they are both, and they are used in very different cases. So one of them is used on one variable to determine if some pre-established pattern is being followed. The other one is used on two variables to determine if they are independent of each other. Okay, so we have a lot of keys or like clues, if you will, to tell us which one to use when. The third test that we are going to talk about today is the ANOVA. The ANOVA is completely unrelated to the chi-squares. It is a test that extends the two sample t-tests to the most general case. So basically what the ANOVA asks is there evidence that mu1 equals mu2 equals mu3 equals mu k, okay? And in this case, k is number of populations. So let's suppose that in a particular illustration, you had 5 different population means, and you wanted to determine if those 5 population means were if there was a difference among those 5 population means. So maybe mu1 is different from mu2, mu1 is different from mu5, mu2 is different from mu3. Some difference exists within that set of population means. This would be the test that we use. So it's a general test for differences among multiple means. So the alternative here is that at least one difference exists. So the ANOVA does not ask mu1 equal mu2 equal mu3 equal mu4 versus mu1 different from mu2, different from mu3, different from mu4. It asks, are the means all equal, or is one combination of means different? So you only need 2 means to be statistically different from each other in order to reject the null hypothesis in an ANOVA experiment. All right, on step 2 of this, we state alpha. On step 3, we compute test statistic, which is F, which is equal to the mean squared treatment divided by the mean squared error. Okay, and this is calculated through a ANOVA table. So the calculation of the test statistic for an ANOVA is based off of what is called an ANOVA table. And this is something that you will see illustrations of in lecture exclusively. But we will work through the calculations of it today in Rcmdr so that you can at least see how the table is structured and how you work with the table. But the specific calculations of the mean squared treatment and the mean squared error, that is how you compute them by hand, will be done in lecture. Okay, so then on step 4, you find critical value and p-value. So here, the degrees of freedom is equal to, for an ANOVA test, we have 2 degrees of freedom for we have 2 degrees of freedom. I'll just write that. Okay. So df1 is the degrees of freedom for the treatments, and df2 is the degrees of freedom for the error. Okay. And again, I'll show you how this works through illustration and then how we use that to compute critical values and p-values in Rcmdr. And then after this, on step 5, we have decision. And then on step 6, we have conclusion. Okay. So we have our 3 tests that are of interest to us in today's lab: chi-square independence test, or sorry, chi-square goodness of fit test, chi-square independence test, and ANOVA. The goodness of fit test is used to determine if there's evidence that data follow a pre-established pattern or distribution. The independence test is used to determine if 2 variables are statistically independent of one another. And then 3, the ANOVA is used to determine if there are pairs of means that are statistically different from each other among a set of means from a population, or among a set of means that have more than 2, among a set of means that is of size greater than 2. All right. So we will switch over to Rcmdr now. All right, so share. Okay, so the 3 problems that we are going to work through from the demo exercises to illustrate how these 3 tests work are exercises 28, exercises 30, and exercise 33, I believe. Exercise 33, yeah. So 28, 30, and 33 are the 3 that we're going to work through today. Okay, so exercise 28 states the overall proportion of Albertans who voted for the 4 major parties in Canada in the 2015 federal election follow below. So we have Conservatives, Green Party, Liberal, and NDP. And then we have the proportion of people in Canada that voted for these parties. So we're saying here, for example, 60.62% of people voted Conservative. 2.57% of people voted Green. 24.96% of people voted Liberal, and 11.85% of people voted NDP. So we are going to take this as being sort of the pre-established distribution of voters. Now, okay. So suppose in the data set where we have the data set full post-election survey for R. Imagine that in that data set, we have a random sample, or we consider that data set to be composed of a random sample of Albertan students. What we are interested in doing is determining if those students in the sample voted in a pattern that follows the distributions given above. So basically what we are asking here is there evidence that the way that our sample voted aligns with how the population voted? So do the proportion of students in the sample match up to, or are they close enough to the proportion of people in the population in terms of how they vote for each party? And this is what the chi-square goodness of fit test is meant to do. It's meant to tell us whether or not we have significant evidence that a sample sort of proportions itself in a way that aligns with some established distribution. So we're interested in determining if our sample's voting habits align with the proportions established by the population. All right, so let's open up Rcmdr. All right, so here is our Rcmdr. So then we have data import from Excel, and we'll call this Q28. Okay. So we have, for me, oh, sorry, I need to go back. Oh, okay. So I'm gonna have to download this from the website real quick. Sorry about that. So I'll just pause this whilst I download. There we go. Okay, so here's our full post-election survey. All right. Now in the question, we are told okay, so we are going to use the column best plat. So you can see from studying this data set, we have 446 total observations in our sample. So our sample size is 446. In the column best plat, you can see that what we have here are just individual outcomes that are associated with each of the variables. So basically, the setup for a chi-square test is actually just to establish counts of the number of times each of the different outcomes occurred. So we have 4 different outcomes in this illustration: liberal, conservative, NDP, or green. So those are the 4 possibilities. The data set is telling us basically just how many people voted for each. Okay, how many liberal votes did we get? How many conservative votes did we get? How many NDP votes did we get? How many green votes did we get? And then what we're going to do is we're going to total those, and we're going to use them to determine if the way that our population votes lines up, or sorry, if the way that our sample votes lines up with the way that that population voted. So if we go back to our Microsoft Word page here, we have, first off, in part A, state your null and alternative hypothesis. Okay, so there's different ways that we can do this. I usually like to work with general statements. So I'll write something like, the data follow the distribution or the proportions in the distribution of interest. Now, another way that you can think about this would be P1 equals 0.6062, comma, P2 equals 0.0257, comma, P3 equals 0.2496, comma, P4 equals 0.1185. So basically what we're asking here is there evidence that the sample that we are working with have the same proportion of voters as the population? So do we have 60%, 60.62% of people voting conservative? Do we have 2.57% of people voting green? Do we have 24.96% of people voting liberal? And do we have 11.85% of people voting NDP? The alternative here would just be that the data do not follow the proportions in the distribution of interest. Okay, so basically the alternative is just that this isn't true. There is no evidence to suggest that these proportions are being met. Now that could mean that one proportion is off and the others are close, or 2 proportions are off and the others are close, or all 4 are just way off. Okay, so we have a lot of different outcomes that could correspond to not following those particular proportions. Okay, state the assumptions and comment on the validity. Okay, the first assumption is that all expected counts are greater than 1. Yep. The second is that at least 20. Okay. At least 20% of expected counts are greater than 5. And 3 is that a simple random sample was collected. Okay, so the next thing we have to do is actually work out what these expected counts are, because that's the only way for us to comment on the validity of them. So in part C, we will compute the expected counts. The way that we compute an expected count for a goodness of fit test is we take sample size and we multiply it by the proportion from that distribution of interest. So here we have 446 multiplied by 0.6062, and that gives us 270.3652. Okay, so that is the first expected count. This is how many of the 446 students in our sample we would expect to vote conservative if our sample follows the population proportions. In the second case, we would take sample size and multiply by the proportion that are expected to vote green, and that would give us 11.4622. In the third column, we would take our sample size and multiply by the proportion expected to vote liberal. And then in our fourth column, we take our sample size and multiply by the proportion that are expected to vote NDP. All right. And then these would become our 4 expected counts. Okay, so now we can, So now what we can do is we can write this one is verified. Okay. No expected count is less than 1. So you can see in the table below, our expected, the lowest expected count that we have is 11.3216 or 11.4622. So, sorry, is 11.3216. So we do not have any expected count less than 1, so that first assumption can be verified. The second assumption is that at least 20% of the expected counts are greater than 5. Okay, well, we have all of our expected counts being greater than 5. So that means that we have 0% of the expected counts being less than 5, so this assumption is verified. And then finally, we have a simple random sample being collected. In the question, we have here, consider to be a random sample, okay? So we can write here that this is verified. From description, all right? So those, for the goodness of fit test and for the independence test that we will see later, these are our 3 assumptions, and we verify the first 2 by computing these expected values, and we verify the last one from sample description. Okay, so now we can start our test. So we have established the null hypothesis. We are told in the question that we are going to test at the 5% significance level. So this is established here. And now what we have to do is compute the test statistic. Okay, so to compute the test statistic, we take the observed count minus the expected count squared and divide by expected. So for example here, what we had leading up to this was 130 minus 270.3652 squared divided by 270.3652 equal to this. Okay, and that's where the 72.824, 8704 comes from, is this process here. So we can do the same thing for each of the different rows below. So here we would have 23 minus 11.4622 squared divided by 11.4622, and that's going to give us 11.6139. And then we're going to follow this same pattern for the row below. And if we do that, we should end up with, oh, sorry, this is 111. And if we follow that below, we should end up with 106.0980. And if we do it for the last entry, we should end up with this. Okay, and then you can check both of these values just by following the process given above. All right. Okay, so then what we do is we just add these values together, these four quantities that correspond to the observed minus expected squared over expected, and our test statistic is shown below. So this 198 is the test statistic for the chi-square goodness of fit test. The degrees of freedom is equal to the number of entries minus 1. So K here, or C as I wrote it before, is number of outcomes, which is 4. Because we have 4 different parties that you could fall into. So this is how you work through the calculation of the test statistic by hand. Now in Rcmdr, of course, we don't have to do this. So we open Rcmdr, and to run this test, we go okay, statistics, summaries, frequency distributions. We select our variable, and then we check this box for chi-square goodness of fit test. So again, to run the goodness of fit test is statistics, summaries, frequency distributions. You select the variable, which is best plat for us, and then you click goodness of fit test. All right. Then it asks you what are the hypothesized probabilities for each of the different outcomes. So here we have 0.6086, I believe. I'm just going to check that. 6062. Here we have 0.0257. Here we have 0.2496. And here we have 0.1185. Okay, and then we click OK. And then at the bottom, it gives us the output that we need. Then we can take this and paste it below. And then it asks us for the output counts as well. So we can take that. I don't really think we need this. We have it above, but whatever. Oops. We can paste that below as well. All right, so from Rcmdr, you can see, first of all, that our test statistic that we calculated by hand here, 198.2639, is very close to what Rcmdr has given us, 198.27. So just a bit of rounding has made a small difference there. You can see that the degrees of freedom, which we established as being 3, because we have 4 categories minus 1, is the degrees of freedom given below. And then you can see that for the p-value, we have a p-value less than 2.2 times e to the negative 16. So basically our p-value is right around 0. So to run this test in R commander, we click statistics, summaries, frequency distributions. We select our variable, and then we check the box for goodness of fit test. Then we click OK. And then inside each of these boxes, we have to state the probabilities that are given in the question. So we had 0.6062 for conservative, 0.0257 for green, 0.2496 for liberal, 0.1185 for NDP. Okay, and then we click OK, and then we end up with the output given below. Okay, so with that being given to us, we can then finish off the test. So report our test statistic, again, 198.27. Report the degrees of freedom, 3. Our p-value statement here is going to be p, that the chi-square value is greater than 198.27. And then the p-value is going to be 2.2 e to the negative 16, which is basically just equal to 0. All right. Okay, so does the evidence lead to rejection of the null hypothesis? Why or why not? So we would certainly reject H0 here. And we would do this since p-value is much less than alpha. And then we can say at the 5% significance level, we have significant evidence that the sample of students, voting patterns do not align with those of the Canadian population from 2015. So basically what we found here is that the data does not give any evidence that our students vote in the same pattern that was established in the 2015 federal election. So that might mean that we don't have as many conservative voters, and then we have more NDP voters. It might mean that we have a ton of green voters and we don't have any voters anywhere else. It could mean a lot of things within the outcomes that are available to us. But the big takeaway is just that the way that the students voted in the sample do not follow the pattern that was established in the 2015 election. Okay, comment on the results. What cells contributed greatly to the test statistic value? What cells did not? How did the observed counts differ from the expected counts? Okay, so when we look at the table here, when it asks us which cells contributed greatly to the test statistic, that would be the cells with the highest values. So the liberal and the conservative cells contributed more information to the test statistic than the green and the NDP cells. So we can say here, the liberal and conservative cells contributed the most, more information than the green and NDP cells, period. The cell that contributed the most information was the liberal cell, and the cell that contributed the least information was the NDP cell. Okay. Okay. How did observed cells differ from expected cells? Okay, so if we look at the original observed measurements, we can see that our highest proportion voted liberal and our lowest proportion voted green, and that we have 130 people voting conservative. So basically what we can see from comparing the observed counts to the proportions here, or actually the observed counts to the expected counts directly, is that we have more students are voting liberal than the population did, and fewer students are voting conservative than the population did. So our observed counts show us that more students prefer the liberal party than the population did, and that fewer students preferred the conservative party than the population did. Okay, all right. Okay, any questions about the goodness of fit test? Okay, so now let's turn our attention to the independence test, and we're going to use exercise 30 for the independence test. Okay. Actually, sorry, one sec. This is sort of. Okay, let's do 31. Let me just check to see which one aligns best with the assignment so that we can focus our attention on that. I would guess it's 31, but. No, we got to do both. Okay. Okay, so let's start with exercise 30, and then we'll have to do 31 as well so you guys can see it. Okay, so in 30, we have a random sample of people are surveyed and then classified according to their age group. So we have 3 outcomes here, below 40, 40 or older, and the likelihood that they would purchase an electronic device that could be calibrated to help them find lost keys. Perform a test of independence to determine if age group and likelihood of purchasing the devices are related. So in the chi-square independence test, we have 2 variables. In this particular illustration, we have age group as one variable, and we have electronic device being purchased as the second variable, specifically electronic devices to help them find lost keys. We want to determine if age group and the likelihood of purchasing the device are related. So in the independence test, we are again trying to determine if there's a relationship between the first variable and the second variable. So our null hypothesis will be that age group and the likelihood of purchasing the device are independent. And this is going to go against the alternative that age group and the likelihood of purchasing the device are not independent. Okay, so the assumptions here are exactly the same as the assumptions that we established before. So we will have no expected counts less than 1, no more than 20% of the expected counts are less than 5, and 3 SRS was collected. Okay, so what we have to do next is, of course, compute these expected counts. So to do this, we will use Rcmdr. So what we will do is in Rcmdr, we will go statistics, contingency tables, enter and analyze two-way table. So in this particular illustration, we are not given the data beforehand. We are being asked to basically perform the whole procedure ourselves. And this is similar to question 4 on assignment A. Okay, so in this particular illustration, you can see that we have 2 age groups, less than 40 and 40 plus. And then we have 5 categories for whether or not they will purchase the device. Very unlikely, unlikely, neutral, likely, and very likely. So we have 2 rows and we have 5 columns. All right. So in the first entry, we're going to type in the value from this table. So here we're going to have 6. Then we'll type in the next value, which is 12, the next value, which is 20, the next value, which is 30, and the next value, which is 15. And you can see I'm literally just taking the values from the table here and I'm plugging them into Rcmdr. Then I'm going to have 5, 8, 26, 42, and 30. All right. Oh, sorry, this is a name. So silly. Age group. Purchase. Okay, then we can click on the, we click OK. All right, and you can see that it gives us the outcome of the Pearson chi-square test directly. So that's actually pretty nice. Let's just go back and see what our options are here. Okay, so if we enter the data and then we click statistics, we can click print expected frequencies. We can also click components of chi-square test, which is nice. So now we click OK. All right, so now we actually have some values that we can work with. All right, and then we need the chi-square, which is given below here. And then these are the cell contributions here. We'll probably have to go back and show that again, but. All right, okay, so here are the expected counts. So you can see the lowest expected count is 4.7, where's my chat? Is 4.70716, is 4.706168. Okay, so this is verified. Lowest count is 4.76. Okay, we have no more than 20% being less than 5. Okay, so we have 12 different, we have 10 values here. So what we are basically asking is that no more than 2 of the 10 values are less than 5. So we have one value less than 5, which is only 10% of the expected counts. So we only have 10% of the expected counts being less than 5. So this is verified as our cutoff is 20%. And then SRS being collected is verified from the experiment. All right. So here are the expected counts for this process. So we can fill these in using what was given to us in Rcmdr. Okay. Here are the cell contributions. So this is basically just telling us how much each of the different cells contributed to the test statistic. It's very strange. Okay, and then finally down here we have the output from the test. I apologize for going fast, but quite a bit to get done. So I'm just trying to squeeze it all in here. Okay, so in part D, we can actually finish the test off using what is given to us in Rcmdr. So our test statistic is 4.730. Our degrees of freedom is 4. The p-value statement is that the chi-square is going to be greater than 4.7308. Okay, and then the p-value is going to be 0.316. Okay, so in this case, we would fail to reject H0. And this is because the p-value is greater than alpha. So then we can say at the 5% significance level, there is significant evidence. There is no significant evidence to suggest that the age group and the likelihood of purchasing the device are not statistically independent. Okay. Okay, in exercise 31, we have the following data set. So this is use software with the file lister to obtain the expected values. Okay, so we need the lister data, which I assume is in the dataset file. Okay, so what we're doing here in exercise 31 is exactly the same as what we were doing in exercise 30. We're running a chi-square independence test, and what we're trying to do is determine if there is evidence that the row variable, which is this with or without carbolic acid, is independent of the column variable, which is whether or not the patient survived. So for context, we have Joseph Lister was a 19th century surgeon who pioneered the use of disinfectants to reduce infection rates. Over the years, he performed 75 amputations, 40 using carbolic acid as a disinfectant and 35 without. Then we have the following results. At the 98% confidence level, determine if the patient's survival or death is independent of whether or not carbolic acid was used during surgery. So our null hypothesis here is going to be that the patient survival and the use of carbolic acid are independent versus the alternative, patient survival and the use of carbolic acid are not independent. Okay, so these are the two outcomes. State the assumptions. So the assumptions are always the same. So we have no expected values are less than 5. And then we have at least 20% of expected values are greater than 5. And then 3, we have SRS. Okay, so what we need to do here is use the software to determine those expected values, right? Because we need those to check the assumptions. So we go back to Rcmdr. Danny, to do that, you go statistics, contingency tables, enter and analyze two-way table, statistics, and then you click on components and print expected values. Okay, so statistics, summaries or contingency tables, contingency tables, statistics, and then you click here. Okay, cool. Okay, so for the lister data, we have to load the data set, right? So data, import from Excel. This is going to be Q31. Click OK. And then lister. All right, so now what we're going to do here for this one, we will go statistics, contingency tables, two-way table. Okay, so we load the data set. So in the first, sorry, just to clarify, in question 30, we had to enter the data on our own. So when we have to enter the data on our own, we go contingency tables, enter and analyze. In 31, we are already given the contingency table beforehand. So if we look at Q31 and we click view, you can see that in this case, we have all of our observations being aligned with their particular outcome. So what we're doing in 31 is we're building the contingency table using the data provided to us. So in this case, we click statistics, contingency tables, two-way table, and then we select our row and column variable. Now in the question, we have carbolic acid on the row and we have patient status on the column, okay? Then we click statistics, we have chi-square, print expected frequency, and components. So the same thing that we did before. We're checking the same boxes. The only difference is that in the first illustration, we had to build the table ourselves. In the second illustration, the data is provided so we can go right to two-way table. So then we click OK, and you can see that it pumps out all the information we need here. So here are the expected counts shown in the second table. Okay, so if we go down here, we have expected counts shown below. All right, now if we look at the expected counts, we can see that all of these are greater than 1. Okay, so the first one is verified. Is 10.26667. And we can see that no expected value is less than 5. So this is verified. No expected values less than 5. Okay, and then SRS we can verify from the description. I assume that somewhere it says. Actually, it's not really clear. All right, so those are the expected values. The cell contributions are given in the last table. So we have chi-square components. Okay, and then the test output is given right here. Okay, so from our commander, we have the test statistic is 8.4952. The degrees of freedom is 1. The p-value statement is p chi-square greater than 8.4952, and the p-value is 0.003561. Okay, so we reject since our p-value is less than alpha, which is 0.02 in this case. So then we can say at the 2% significance level, there is significant evidence that the status of the patient is independent of whether or not the carbolic acid is used. That is, patient status is dependent on the use of carbolic acid. All right. Okay, so the last thing we need to look at is the example of how to use the ANOVA, which we can do using question 33. Let me just check something. Okay, we'll use 34 to do this one. Let me just check something else here. So we still have just about 20 minutes, so we should be fine. I apologize again for having to rush a little bit. This was it was just tough to pace it, I guess. Okay, so we should be good with 34. So in question 34, we're going to use Allen's lab exam grades fall 2019. So let me see if I have this data set loaded already. So we have data, import from Excel. This is Q34. Allen's midterm. No, I need to grab this one as well. So this is the Allen's lab exam grades. There it is, first one. Save. Okay, so We have looked at one example of how to do the goodness of fit test. We have looked at two examples of how to perform a chi-square independence test. And now we're looking at one example of how to conduct the ANOVA. So again, those three tests are very different. The chi-square tests are the same in that they both use the chi-square distribution and that their structure in terms of building the test statistic and whatnot is identical, but they are different in what they ask. And now the ANOVA is very different to what we are utilizing in this particular experiment. No, Danny, the ANOVA is not included on assignments, on the next assignment at all. Yeah, it's ANOVA's next week's assignment. But we have to do the ANOVA today because they want to put it on Lab Quiz 5, or because it's on Lab Quiz 5. So that's what's going on. Right, so with the ANOVA, we are basically asking if there's evidence of mean equality. So mu1 equals mu2 equals mu3 equals mu4, up to however many means are available, versus the alternative that some difference exists among a combination of the means. All right, so Alan taught 3 sections of 151 during fall 2019. The lab times were Tuesday AM, Thursday AM, and Monday AM. At the end of the semester, all students in STEP 151 wrote a common lab final exam worth 61 marks. The lab grades for all the students in all 3 of Alan's sections can be found in the final exam, Alan's lab exam grades, fall 2019. The column time of day contains the time the exam was written, and the column grades contain the student's grade on the lab exam. Alan was curious to see if the mean grades from the lab exams on different days would be the same. Assuming these results are representative of populations of students writing at the indicated times, perform a one-way ANOVA test to determine if the mean grades are equal at 3 various times. So what we are saying here is, suppose that we have 3 populations: Tuesday morning, Thursday morning, and Monday morning. So Tuesday AM, Thursday AM, and Monday AM. So those are the 3 populations. Each of those populations have their own mean score on the final exam. What we are interested in determining is if there is evidence that the mean score at between Tuesday morning, Thursday morning, and Monday morning are different, or at least one pair of differences exists. So in this situation, we have H naught. So I need to, is there a mu anywhere that I can snag? Okay. So we'll have mean underscore Tuesday AM equals mean underscore Thursday AM equals mean underscore Monday AM. Okay, so that is the null hypothesis, equivalence between the population means of the 3 different times. And this is against the alternative, at least 2 means are different. Okay, so the ANOVA tests for mean equality versus the alternative that at least 2 of the means are different from each other. So it's not equality versus complete inequality. It's equality versus some pair of means are different. Okay. Okay, state the assumptions of said test. All right, so we have random samples of observations are drawn from each population. So we have random samples for each population. The samples are independent of one another. So kind of like an extension of a independent 2-sample t-test. The populations are normally distributed, and 4 the populations have equal variance. Sorry, I'll be right back. I need to use the facility. Okay, so our 4 assumptions are very similar to the independent 2-sample t-test. We the big difference here though is that we assume equal variance. So we assume that all 3 populations have the same size or have the same variance. Use software to obtain an ANOVA table from which you can determine if at least one of the means differ from each other. Okay, so what we're doing here is we are using Rcmdr to find the test statistic. So as I mentioned earlier, the way that a test statistic is computed for an ANOVA is through what is called an ANOVA table. So in Rcmdr, to find the ANOVA table, we would first load our data set, which is going to be data import from Excel. This is Q34, click OK. We have Allen lab exam final grade. All right, we can click view. So you can see here the way that the data is structured. We have the time the exam was written, and then we have the grade on the exam, and it's separated for each of the different time points. So to run the ANOVA, we click statistics, means, one-way ANOVA, and then we group by time of day, and our response is the grade on the test. We don't click either of these things, and our confidence level is 0.05. So we have 0.95 as the confidence level here. Click OK. And then here is the ANOVA table. Okay, so what we have is degrees of freedom. We have sum of square. We have mean squares. We have F. All right, like this. Okay, so this is the ANOVA table. So you can see we have time of day and residual here. We have degrees of freedom, sum of square, mean square, F value, and the probability here. And under each of these, we have those specific values, right? So what we're saying is like the sum of square for time of day is 1,749. The sum of square for residual is 11,896. The mean square for time of day is 874.6. The mean square for residual is 158.6. The F value for the test is 5.514. So this is our test statistic. And this last value here, probability greater than F, 0.00583, that's the P value. All right, so this part here is the P value. Now you can see that there's a double star beside the P value. That's telling you the significance level it's actually significant at. So what this is telling us is that we actually have statistical significance of a difference at the 0.01% level. Okay, so the test stat based off the table is 5.514. The DF for an ANOVA test, we have 2 degrees of freedom. So we have 2,75. So we have 2 degrees of freedom here. And the reason why will be made clear in lecture when we show you how the table works, but you need 2 rather than 1 DF for an ANOVA. The P value is given by 5.514. Okay, so that's our p-value statement, and the p-value itself is 0.00583. Okay, so we will reject H0 because our p-value is less than the significance level. Okay, so we have at the 5% significance level, there is significant evidence that the final grade, that the average final grade between the 3 lecture times, or sorry, there is significant evidence that at least 2 of the average final grades between the 3 lecture times are different. So again, the alternative for an ANOVA is not general inequality, so that it's not that all of the means are different from each other. It's at least 2 of the however many means there are different. So in this case, what we have found evidence of is that at least 2 of those means are statistically different. So it could be that the Tuesday morning and the Thursday morning are different, or that the Thursday morning and the Monday morning are different, or that the Tuesday morning and the Monday morning are different. We don't know exactly which pairs are different, but we know that a difference exists. Use software to find the critical value for your significance level, paste the output. Okay, so to find the critical value for an F-test using Rcmdr, we type distributions, continuous, F distribution, F quantiles. Okay, so this is very similar to how we found critical values for the normal and the student T. So basically all we're doing here is we're finding an F value on a particular distribution. So distributions, continuous, F quantiles. Okay, the probability here is 0.95, or here, let's do it properly. So 0.05, and it's an upper tail probability because we're talking about a rejection region. The numerator is 2 degrees of freedom, so that was the first DF, and the denominator is 75 degrees of freedom, which was the second DF. Then we click OK, and we end up with the following. All right. So based off of this, we can reject H0 if test statistic is greater than critical value. So one of the nice things about an ANOVA is that we don't have the concept of being two-sided or one-sided. So we can always use the exact same rule. We will always reject if the test statistic is bigger than the critical value anytime we use an ANOVA. So based off the critical value approach, we would reject H0 since 5.514 is greater than 3.118642. Okay, and then the p-value approach, we already did this above. So again, p-value, we would reject H0 since p-value is less than alpha. All right, and then in G, same thing as before. So we conclude there is significant evidence that a difference exists among the population mean scores on the lab finals. And then there's a little note about those differences. Oh, and that's the end of the demo stuff. Okay, we did it. So I have a few minutes left here. Does anyone have any questions? Okay. All right, well, if there's no questions, then I will wrap up today's lab. Of course, I'm going to post this. I'll send out the materials and whatnot. And the ANOVA stuff is not for the assignment due this week. This week is only the chi-square stuff, but the ANOVA stuff will be asked on the lab quiz. So that will be, you will be tested on that next week. And then the next assignment will contain ANOVA materials. So have a good week, everyone. If you have any questions, as always, please let me know. And otherwise, good luck with the assignments and whatnot. And I'll talk to you guys next Tuesday.